On Thursday, we defined momentum in a couple of ways. Does anybody remember either of those definitions for momentum? There is the way that we normally think of the term momentum, but then there's the way that we actually define it scientifically. Either one of those is good here today. Travis? No, that's, you're close though. Okay, the desire of an object, and we use that term loosely, desire of an object, but I know what you mean. To keep doing what it's doing, that's not momentum, that's inertia, right? The tendency of an object to keep doing what it's doing is inertia. And it's real close to momentum, but not quite the same thing. Yep. Okay, the real definition, the scientific definition of momentum is the product of an object's mass and velocity. And because we define it as a product of mass and velocity, we can write out the equation right now, m times v for momentum. Now, what's the other way we define it? The way that we usually think of momentum, the way that we understand momentum. Yep, Patrick? Good. How hard it is to stop something. The harder it is to stop something, the more momentum it has. A train going down the tracks is really hard to stop. It doesn't matter how fast it's going. It's really hard to stop because it's heavy. A bicycle traveling down the road at 50 kilometers per hour is hard to stop as well. Not because it's heavy, but because it's got a lot of velocity. Okay? So things are hard to stop because of mass and because of velocity. And that's where this definition comes from, right? It's harder to stop when you've got a lot of mass and you've got a lot of velocity. Now, Travis, you mentioned the tendency of an object to keep doing what it's doing. That's inertia. Now, if an object is moving, it wants to keep moving. It doesn't want to stop, right? That's like momentum. But if an object is at rest, it also wants to stay at rest. It wants to keep doing what it's doing. That doesn't have any momentum. So inertia and momentum real closely related. Inertia related to mass, momentum related to mass and velocity. Inertia has nothing to do with how fast it's moving. Okay, it has a lot of inertia if it's at rest or if it's moving. Doesn't matter as long as it has a lot of mass. Okay, we wrote down this equation for momentum already. This comes back to the definition. What are the units that we're going to use for mass here? Kilograms. Somebody in one of the classes on Thursday, and I can't remember which class it was, this one or another one, said, can we use grams for this? I said, well, no, normally we don't use grams. The person had grams and they had kilometers per hour for velocity. Which units for velocity should we use? Meters per second. And then, of course, when we multiply those together, we get kilograms meters per second. The person on Thursday said, can we use grams and kilometers per hour? Or grams and, I forget what it was, centimeters per second or something like that? Like, well, no, not normally, but technically, yes. Technically, if you use grams for mass and, say, kilometers per hour for velocity, you could do that, but the units for momentum would be grams times kilometers per hour instead of kilograms times meters per second. Does that make sense? Okay, my recommendation, though, is, even though that's technically correct, don't do that. Okay, that's my recommendation because in all likelihood, if you start doing that, you're going to mess up sometime and get a wrong answer simply because you didn't convert. Okay, that's correct, but it's not something that you should get in the habit of doing. Okay, let's go with the standard units, kilograms and meters per second. All right, we had worksheet number 1 that was due for today. I'm going to put up the answers for the first 4 questions of worksheet number 1 right now. Have a look at them. See if there's any of those 4 questions you need to go over here. I'll spend a couple minutes doing that. Once you've taken a look at 1 to 4, then we'll take a look at the rest of the questions, see if there's any issues with those ones as well, okay? 1 to 4 are good? Okay, let's have a look at 5, 6, 7, 8, 9 then. Have a look at those answers. Don't worry about the solutions right now, just the answers. If you had trouble getting any of those answers or didn't get any of those answers, then just let me know and we'll go over 1 or more of those as well. Okay, I had some requests to do question 5, 7, and 8 here. So let's do that now. Question 5 says, a 5-kilogram ball accelerates at a rate of 2.0 meters per second squared for 1.5 seconds. What's the ball's momentum after the acceleration? Hey, remember on Thursday when we talked about these problems, or any other problems for that matter, we said in Physics 30 especially, the first thing that we'll do is not so much writing down our givens. The first thing we'll do is just look at the big picture. Okay? Look at the question. See what's going on in the question, and then write down some givens as appropriate, okay? What's going on in this question here? What do we have happening here? The ball is accelerating, right? It's an acceleration problem. But then we want to find the momentum at the end of that acceleration. So it's kind of like a two problem again, where we have to do something with it speeding up, and we have to do something after it has sped up. Kind of like that question we did as an example where we dropped the object. We had to deal with its falling, and then we had to deal with the momentum at the end of the problem. Right? Let's write down our givens in two stages here. Okay, the first stage is the acceleration phase. Okay, in the second phase is, we'll say it's the momentum at the end of the problem here, okay? During the acceleration phase, of course, the mass is 5 kilograms. It remains 5 kilograms through the whole problem. The acceleration is 2.00 meters per second squared. The time here is 1.50 seconds. Okay, it looks like all we have here is that. At the end of the problem, we want to find the momentum. Okay, maybe we want to call it the final momentum because it's the momentum at the end of the problem, right? We want to find the momentum. We know it's going to be m times v. The only equation we have that describes momentum, at least right now, m times v. We've got the mass, 5 kilograms, but we don't know what v is. At the end of the problem, what is v? What are we going to do up here in the acceleration phase to get the final velocity, the velocity at the end of this problem? Yeah, go ahead. I'm sorry? Okay, so we're going to use a is equal to delta v over delta t. Rearrange that. We get delta v is equal to a times delta t. Now, vi is 0, presumably. It should say it starts at rest. It doesn't. But that's what we meant here, I think. Relatively clear. So if vi is 0, then delta v, the change in velocity, is the same as the final, right? If we get the change in velocity and the initial was 0, then delta v will be the same as vf. So it's going to be a times t, 2.00 times a time of 1.50 seconds. That's going to give you 3 meters per second. Now we're going to multiply 5 kilograms times 3 meters per second. And that's going to give me 15.0 kilograms meters per second. Good? How many people got that one? Good, good. I wouldn't say that that's a straightforward question. A straightforward question would be, here's the mass, here's the velocity, find the momentum. That's an easy question, right? This is a step above. It's not a crazy hard question. Okay, we've got to be able to do these questions, but it's definitely a step above that simple, here's mass, here's the velocity, okay? 6, a 2-kilogram rock is dropped from the top of a 30-meter high building. What's the ball's momentum when it strikes the ground? This is real similar to that example question we did, isn't it? And quite similar to the question we just did, question number 5. We've got a couple of things happening here as well. It's falling. And then we have a collision at the end where we want to find the momentum at the end of the problem here. When it's falling, we know that A, not 2.00 like it was in the last question, A is negative 9.81 meters per second squared. It's dropped from the top of a 30-meter high building. If it's dropped, then VI is going to be what? If it's thrown, then VI is something. If it's dropped, Matt, then VI is good. VI is 0 meters per second. My displacement here is neg 30 meters. Why is it negative? Because it's downward. It falls downward, right? Having said that, if we defined down as positive, we could make it positive 30, but if we did that, we'd have to make A positive 9.81. We tend to avoid doing that because we're used to making A negative 9.81. That's all we have, I think, for that part of it. The collision with the ground, we want to find the momentum. So same kind of idea here. P is equal to m times v. Was it 6 we had to do? I think I think it was 7 and 8, wasn't it? Okay, we're almost done this, so let's keep doing it. 2 kilograms times VF, we don't know, but we're going to do the same thing here as we did on Thursday. VI squared plus 2AD. Okay, that gets rid of the square there. Solve for VF. Not sure what it works out to be off the top of my head, but okay. Take that number, plug it in here, and that's going to give us our momentum. We'll skip through that pretty quick since you didn't ask me to go over that question. Is that good? All right, number 7. This is one that you did ask me to go over. A 1 kilogram rock is thrown up into the air from ground level at a speed of 8 meters per second. The ball travels up to a max height, then returns down to the ground. So picture it now. The ball is being thrown up in the air. It goes up. As it goes up, you know, it slows down. What rate does it slow down at, by the way? 9.81 meters per second squared, right? It decelerates at 9.81 meters per second squared until it comes to a stop. But gravity doesn't disappear, so even when it stops, what happens to it? Sorry? It comes back down, right? It starts to fall. And what rate does it fall back down? Negative 9.81. So if it slowed down at 9.81 on its trip up, and it sped up at 9.81 on its trip down, what do we know about the speed that it was thrown at versus the speed that it ends up at the ground at? In other words, if I throw it upwards at 8 meters per second and it slows down for a certain amount of time at 9.81, and then it stops and it speeds up at 9.81 for the same amount of time, how fast is it moving when it hits the ground again? 8 meters per second, but it would be downwards, right? So negative 8 meters per second. In this question, all we're going to have to do is say P is equal to m times v, because we know the velocity. We know how fast it's moving when it hits the ground. Okay, mass is 1 kilogram times negative 8.00 meters per second, which gives me negative 8 kilograms meters per second. We didn't even write down givens here. Should we have? Yeah, we should have, really. Okay, but once we looked at the big picture of the question, once we saw what was happening in the question, it was an easy question at that point, right? The hard part of it was kind of seeing what was going on in the question. Okay? The hard part and the most important part was looking at the big picture in the question. And finally, question number 8. By the way, please stop me if I happen to go too fast through a question. We'll spend as much time as we need to. If I think that everyone gets it and they don't, just let me know and we'll spend some more time on it. Number 8 says, a 1.5 kilogram rock is thrown up into the air from ground level. It reaches a max height of 7 meters, then returns to the ground. What's the rock's momentum as it strikes the ground? Big picture, what's going on here? The rock is going up. When it reaches a max height, what's its speed here when it reaches that max height? 0, it stops, right? And then it comes back down and hits the ground at a certain speed. This is not quite like some of the questions we've done. A question like number 6, where we dropped an object, right? Because we're throwing the object up and then it's coming back down. But we can turn it into one of those questions. You think about this. We're throwing the object up into the air, it stops, and then it comes back down. How different is that from just dropping it from that height in the first place? Let's not analyze the whole thing here. Let's not analyze the trip up and down. Let's analyze the trip down. What's the ball's momentum as it strikes the ground? Let's pretend that it was dropped from a height of 7 meters. In that case, we'd say VI is equal to 0 meters per second. Right? In the whole problem, it's not. But during the fall, VI is 0 meters per second, the same as it was in question 6. We also know that during that fall, A is neg 9.81 meters per second squared, and the displacement is neg 7 meters. During the collision with the ground, we're looking for the momentum. This is identical to question number 6 now. But again, how do we see that? It's because we looked at the problem first instead of just writing down numbers first. Had we wrote down numbers here, okay, we probably would have struggled with this. And those of you who had got this question wrong, that's probably what happened. You get too focused on writing down your givens, writing down your numbers without looking at the bigger picture of the problem. Okay, so PF is equal to m times vf. We're going to find vf by doing the square root of vi squared plus 2ad. Vi is 0. So it becomes the square root of 2 times neg 9.81 times neg 7.00. Again, we're analyzing only the fall here, not the trip up and down, but just the trip down. Is that okay to do? Sure it is. If all my numbers are right for the trip down, that's okay. You get a number there for VF. We plug it in there, and we get what we need there. How many people got number 8 correct? Good. Excellent. That's a good question. That's a good question. I think a question like number 5 or number 6, they're doable questions, and they're harder than, the simple P equals MV question. Question like number 8 is a good question because you got to think a little bit past that, right? It's not just, the same old thing as we've done 3 or 4 times before. Good are those? All right. I would like you right now, please, to take a quick look at multiple choice question number 2. This would be numeric response question number 2, I suppose. You do not need to submit the answer to this one because it's numerical response. Okay, just do the question here for the next 60 seconds or so, and then we'll take a look at it as a group when you're finished there, okay? Okay, we've got a couple of different answers here. A number of people said 5.56, a number of people said 6. The answer is 5.56. Now, how do we get that, and why is 6 not right? Well, if you've got 6, in all likelihood, you did the question right. You knew exactly what you were doing if you got 6, but you expressed it wrong. And that's the main reason why I wanted to do this question. Okay, this question is not a particularly difficult question, right? P is equal to m times v. We got to remember to convert kilometers per hour to meters per second. But in the end, the challenging thing about this for you guys right now is just how to express it. It says b times 10 to the... Let's do the question first here. P is equal to m times v. Clearly, it's just a straight momentum question. P is equal to m times v. Probably a good idea when we see this right off the top, though, is to circle kilometers per hour in red or to highlight it in pink or some color that will draw attention to it. Because we don't want to forget to do that conversion. We don't want to forget to convert that to meters per second. You guys remember how to do that conversion? Kilometers per hour to meters per second is? Good. Divide it by 3.6. When we do that, and then we multiply it by 1 times 10 to the 9, we will get a momentum of 5.56 times 10 to the what? 10 to the 9? Kilograms meters per second. Now, a very, very common mistake here is when we see this B times 10 to the W, we think, well, it's got to be 1 digit, right? So we round 5.56 to 6. But let me give you this one. Let's do this one. What's x equal there? What's x equal? 3 divided by 2 is 1.5. Look, if x can be a decimal number, 1.5, then why can't b be a decimal number? Okay, we're looking for the value of b, the base of the exponent, 5.56 times 10 to the 9. They tell me right here it's a 3-digit answer, a 3-digit answer, so it's going to be 5.56. Okay, don't drop the decimal point, just write down the base. B times 10 to the W is always the entire base of the scientific notation. Okay? All right, I got another example for you. This one is a bit different, though. This one involves a process that I call variable value changing. We're changing the value of a variable without knowing what the value of the variable was to begin with. Here's the momentum of the object. We want to find the momentum of the object if we make some changes to it. If we change the mass, make it 1/3 of what it was, and we change the velocity, we're increasing the speed by a factor of 4. We're making these changes to the variables without knowing what the values were to begin with. How do we How do we increase the speed by a factor of 4 when we don't know what the speed was? If it was 2, we can make it 8. That's easy. But if we don't know what it was, how do we multiply that by 4? And similarly, how do we divide the mass by 3? It's not really that hard, actually. Clearly, the concept involved here is momentum. Okay, and it is this variable value changing type question where we're changing the values of variables without knowing what they were to begin with. So let me walk you through this process here, okay? We're going to pick an equation that's relevant. And clearly that equation here, the relevant equation here is going to be m times v. Right? It's the only equation we have for momentum, and even if we had more, we know momentum is m times v. I'm going to put a little subscript beside the momentum node, the P. I'm going to put a subscript O. What do you think that O stands for? The original amount or the old amount. Okay, whatever we start with. Okay, this is what we start with. The original momentum is m times v, but it's also equal to 2.45 times 10 to the 2. Okay? Nothing rocket science here yet. Really, we're just writing down what we're told. We're told that we start off with 2.45 times 10 to the 2 kilograms meters per second of momentum. And we know from our data sheet that that's got to be equal to m times v. So we're not going out on a limb here yet. This is where we start doing something new. This is where we have to do something ourselves. Pn. What do you think the n stands for? New. The new momentum. After I make my changes. Listen carefully to what I'm about to say here. Momentum is not m times v. Momentum is mass times velocity. That's the equation for momentum. It's mass times velocity. We represent mass times velocity usually by saying m times v. Does that make sense? It's not really mv. It's really mass times velocity. We simply represent it as m times v usually. But we could call mass q. And we could call speed r. And then momentum would be q times r, right? Would that be okay? Sure, as long as it's still mass times velocity, that would be okay. Okay, the momentum was represented by m times v, but now it's not. Now the momentum is going to be represented by 1/3 m, because the mass isn't m anymore. The mass is now 1/3 m. And the velocity is no longer v. The velocity is 4v. So we said a second ago momentum was m times v. Now we're saying momentum is 1/3 m times 4v. Yeah, it's okay. Momentum is not really m times v. We just represented it that way. Now we're representing it differently. It's still mass times velocity, but it's a new mass, and it's a new velocity. Now what I want to do is factor those numbers. Quick question for you. What's 1 times 2 times 3? Logan? 6. Good. Okay. Or and what's 3 times 2 times 1? Good. Max, what's 2 times 1 times 3? Good. The point there is that it doesn't matter what order we multiply those numbers in, we still get 6, right? 1/3 times m times 4 times v is exactly the same thing as saying 1/3 times 4 times m times v. Does that make sense? If it didn't matter what order we multiplied 1 times 2 times 3 in, then it doesn't matter what order we multiply 1/3 m 4v in. Let's change the order of them. The only reason we're doing that is to simplify it a little bit. Okay, 1/3 times 4 is 4/3. MV, you with me so far? Now, this is not the hard part. We've just done the hard part. But it is the crux of what we're doing here. We know what MV equals. MV equals 2.45 times 10 to the 2. That's the very first thing we wrote down. We know what its value is. So let's now say 4/3, and then we'll sub in not m times v, but the value of mv, 2.45 times 10 to the 2. That works out to be 3.27 times 10 to the 2 kilograms meters per second. And that's my answer. Does that make some sense? Okay, the key here is to recognize that it's okay for momentum to be m times v, but it's also okay for momentum to be 1/3 m times 4v. We're not messing anything up here. We're not changing the laws of physics by making momentum 1/3 m times 4v. Nobody ever said that momentum is m times v. Momentum is mass times velocity, not m times v. We just represented it as m times v. Well, now we're not. Now we're representing it as 1/3 m and 4v. But it's still mass times velocity. It's just new mass times new velocity. That's all. Travis? Yeah. Okay. You guys feel like you could handle one or two of these questions? All right. Let's give it a try then. Okay, let's see what we can do with these two questions on page 452. The answers are not shown down here. If I scroll down, you'll see them, but I'm not going to scroll down right now. Okay, I don't want you to see the answers right now. Do the questions, then I'll scroll down and we can take a look at the answers, okay? So before you get going on this, there's one thing that I remember actually from when we were doing these questions another time, just a source of confusion here. They didn't mean this to be a source of confusion, but it ends up being a source of confusion. I think it's a typo, but we're going to go with the way that it's actually written. It says here its mass is decreased by a factor of 3/4. That makes its new mass what? What is it? Yeah, instead of being 3/4 m, when we go to substitute into that second expression, it would be 1/4 m, right? We decreased it by 3/4. If we decreased, we don't care what we decreased it by. We care what we have now. What do we have now? Well, 1/4 of what we had before. Okay, so don't forget that when you're going to do these questions, okay? Let's take a look at question number 2 here. It says, during one part of the liftoff of a model rocket, its momentum increases by a factor of 4 while its mass is halved. The velocity of the rocket initially is 8.5 up. What's the velocity during that time interval, the final velocity during that time interval? So what's the velocity changed by when we're making these other changes to these variables? We're making changes to variables. We don't know what the values were to begin with. So we're going to use this variable value changing technique. My equation for number 2 is going to be P is equal to m times v. But since we're trying to find the effect on velocity, not on momentum, then I want to rearrange that equation. Solve for the variable that you're actually looking for. V is equal to P over m. Now, my original velocity we have given to us as 8.5. My new velocity, what does it become? Well, we said it was P over m. Was it really P over m? No, it was momentum over mass. It's still momentum over mass, but the momentum is now going to be represented by this symbol, not P, but rather 4P, because we increased it by a factor of 4. Now the mass is halved. So it's 1/2 of what it was. Now 4 divided by 1/2 is 8. And we already know the value of P over m. It's 8.5. So we're going to say 8 times 8.5. And when we multiply those together, we get 68 meters per second. How many people got that? Good. Excellent. Guys feel like you're in pretty good shape with this stuff? Questions like this, not necessarily involving the momentum equation. Okay, we're going to learn a lot of equations this year, obviously. Questions like this involving any equation, but this technique, this variable value changing technique, they're pretty common. Okay, we see those pretty common. I can promise you that you'll see it at least a couple of times on unit tests this year. Okay, and I mean, as far as the diploma exam goes, I have no idea, right? But probably a pretty good chance that you'll see something like this. It was, okay. Pretty good chance you'll see it again. It's pretty common. Okay. So homework for tonight. And we may have an opportunity to work on this a little bit later here today. Homework for tonight will be page 453, number 1 to 2, 5 to 9, 11, and 13 to 16.